Hello and welcome to the next episode of VELOVirtual. Here we're going to be talking about optimal design meeting limitless manufacturing. I'm really excited to be here today to talk about this one. In this episode, we're focusing on synergy. And this is specifically the synergy between advanced software and the latest manufacturing solutions to drive higher performance. From our experience in the additive manufacturing community, the companies that become the most successful at implementing a strategy of additive manufacturing are the ones that push the limits of design. And Launcher, a manufacturer of high-performance rockets, is a great example of this. They're developing the world's most efficient rocket to deliver small satellites into orbit. And one of the critical elements of boosting performance in rockets like this often lies in the turbomachinery pumps that inject propellant into the combustion chambers. At the heart of those pumps lies an impeller and usually a volute outlet. Spinning at 30,000 RPMs and exposed to cryogenic temperatures, that impeller design is critical to the performance of these pumps. To achieve their goals, Launcher leveraged Ansys CFX software to reach a fully optimized design by quickly simulating the performance. And however, this design also required the right manufacturing solution. So those are the things that we're going to be talking about today. Before I get into that, all right, now I'm excited to introduce our speakers today. So Max Hout is the founder and CEO of Launcher. Max leads their effort to develop the world's most efficient rocket to deliver small satellites to orbit. He's originally from Belgium, but has always had an entrepreneurial spirit with interest in video, technology, space. In his own words, his true passion and long-term adventure is to contribute to space exploration. When Max started Launcher at the end of 2017, he did so with a focus on leveraging the industry's most advanced, proven design approaches and technologies combined with a cost-effective production methods possible by 3D printing advances. So again, that synergy theme. His first initiative was to create a rocket engine capable of producing 22,000 pounds of thrust within 4 years for less than $10 million. And Max has over 20 years of experience as an entrepreneur and it has a lifetime passion for space. Also joining us today from Launcher is Andre. Andre is a mechanical engineer at Launcher. He received his Bachelor of Science in Mechanical Engineering from Yale University and was previously an intern at companies like SpaceX and Tesla. He is currently completing his master's degree in aerospace engineering at Georgia Institute of Technology. We also have from Ansys, Sunil Patil. He's Ansys's industry lead for turbomachinery and propulsion. He previously worked as a design engineer at GE Global Research and is serving as an associate editor at the ASME Journal of Engineering for Gas Turbines and Power. Sunil holds a PhD in mechanical engineering from Virginia Tech. And Gene Miller. Gene is a senior applications engineer at Velo3D. He joined Velo3D in 2016 as a process engineer, working on developing Velo3D's hallmark support-free metal-laying processes. Prior to joining Velo3D, he held various positions in foundry and process engineering. And Gene holds a Bachelor of Science in Mechanical Engineering from Colorado State University. And at this point, Max, I'll turn it over to you.
Great. Well, thank you, Michael, for the chance to present, and thank you everyone on this webinar for taking the time out of your day to learn about our work in developing our E2 engine and our work in 3D printing with Velo3D. As Michael mentioned, I'm Max Hout, founder and CEO at Launcher, and I'm joined by my colleague, Andrei Vankovic, who is the lead engineer that has taken this pump from drawing to hardware and manage all the test program at NASA Stennis, which we'll talk about. Great. So a quick introduction about Launcher. So Launcher is developing an orbital launch vehicle called Launcher Light. We're in the middle of the development program, and our goal is to fly about first test flight in 2024. The key differentiator is that we are focused on the nexus of low cost and highest performance when benchmarked against all the other small launcher that are in development or flying today. The key to high performance and the key to the strategy is obviously not only the engine that we are developing, but the LOX turbo pump that we'll be focusing most of the discussion today on. So to take a step back, give you some context of how the turbopump will be used. So this is a render of the vehicle we are building. It's called Launcher Light. As I mentioned, first flight 2024. It's a small vehicle, but with a useful payload of 150 kilogram to low Earth orbit. It has 3 stages, so 2 main stage and a kick stage. And we are in development, with most of the development work being focused on achieving the propulsion objectives we have. The key to our strategy is the Launcher E2 engine, and you can see there a render in, as most liquid rocket engine, there are really 2 key components in an engine. The first one is a combustion chamber and injector, and we'll talk a little bit about that briefly. And then the second one is the turbopump, which is the focus of today in the work we've done with VELOVirtual and Ansys. It is 22,000 pound in thrust, which is on the largest size for small launcher, which allow us to fly Launcher Light with a single one of them on the first stage, which is critical for being low cost and obviously fast turnaround, as we have to manufacture, test, and qualify 1 turbopump, 1 liquid rocket engine. It used proven LOX-RP1 technology. And in terms of performance, it used the most advanced liquid rocket engine cycle, which is the stage combustion cycle, the closed cycle, whereby all of the gas used to generate power in the pump through the turbine are not dumped overboard and unused for thrust, but are actually injected into the combustion chamber after the turbine and are fully accelerated to generate the full thrust. And so that type of cycle is the most difficult and requires the highest performance and the highest pressure for the liquid oxygen turbopump. Very high efficiency goal that we've proven subscale. As I mentioned, we are developing this engine, copper alloy for highest performance combustion chamber, and a unique LOX cooling. So the program and all the testing and all the work with Velo, you'll see, has been accelerated thanks to an Air Force SBIR of 1.5 million. The check says 750K, but this was increased the same day to 1.5 million in November 2019, which now is managed by the Space Force. And with this program, we tested both the pressure-fed E2 combustion chamber and the LOX pump and turbine, which we'll speak about. As part of that, for our test site, Launcher is a company. We originally were in New York. We now relocated and are setting up our factory and headquarters in Hawthorne in the Los Angeles South Bay area, where we are now. But our test site is now at NASA Stennis Space Center in New Orleans. And there we did both our first testing of our combustion chamber and the liquid oxygen pump testing. This is a combustion chamber, also 3D printed. This is the assembly of the combustion chamber in October last year with Andre, the control room. And this is a photo of the first test fire of the E2 engine combustion chamber that we successfully performed. Now, moving on to the turbopump. So if we look at any liquid rocket engine that is capable of reaching orbit, the turbopump is basically one of the most challenging part of the project, or at the very least half of the challenge. And if you talk about a turbopump for stage combustion closed cycle, that level of challenge even increase. And so our approach has been in 2017, we licensed a proven design that has gone already more than 70 times to orbit, which is a second stage steering engine of the Zenit launch vehicle, which is originally designed in Ukraine. And we licensed the drawings, so no hardware from this location of this proven pump. We actually customized the flow path using Ansys CFX. And then we imported it with State Department approval and State Department and Ukrainian government export approval, imported the drawings and then manufactured and tested it with the help of VELOVirtual. The pressure rise from this pump is 4,000 PSI, which is significantly higher than anything that anyone is doing in open cycle pump. And the main reason why this type of pressure is required is because we are basically not exhausting to the atmosphere after the turbine, we need enough pressure to then integrate the gas from the turbine into the combustion chamber. And that's the key to the stage combustion cycle. Now, this is the first part we produce, which is the Inconel inlet housing, 3D printed in a single piece, including a volute. This is lightly machined after, but this is printed on the VELO3D Sapphire system. This is a mock-up of the inlet housing, which is in aluminum, and at the top, that same part, the outlet housing. So this is our test stand, which I mentioned is the E-complex at NASA Stennis Space Center, a very capable team and very capable test stand, a great asset to our country. And by the way, you might detect an accent, and we heard that I'm originally from Belgium, but I'm a thankful naturalized US citizen. And this is the turbopump assembly, the LOX turbopump assembly that we 3D printed and tested. You can see, if you see my mouse on this side, we have the LOX turbopump, which is in flight-ready design in terms of mass and obviously specification. And this part is the turbine. It's a radial turbine that we are using to drive the pump in this test. And this turbine is traditionally machined in the current state and is not flight weight. But the next step on the development of the turbine after the successful test we had is a 3D Velo 3D Inconel housing to integrate the flow path that we tested in this. So to give you a little context of the test article that we are seeing on the test stand and the render of the engine that we are developing, you can see right here, this is the liquid oxygen pump. This is the whole turbopump assembly. And right here, you see the same part there. And then the turbine, which in this case exhausts into the combustion chamber. And in the case of this test, exhausts to the atmosphere. And you can see the turbine there. Let me show you the first test. So this is the first 10-second test of the article. Andre will take you through some of the more detail in terms of the flow, but the high level is we actuating the turbine with gaseous nitrogen, and we have liquid oxygen coming in at low pressure on the input, and then being exhausted to the atmosphere on the high pressure side, which is this part. So let's So this was our first test, also the first turbopump test for launcher. And it was fully successful. It was the first of many tests, which Andre will now cover. And I want to point out how significant this is. We're dealing with a liquid oxygen media in the pump at 30,000 RPM, about 1 megawatt of power from the turbine. And in this type of environment, in 4,000 PSI discharge pressure, any anomaly, any rubbing between the rotor and the stator can result in an immediate, rapid, unplanned disassembly. And as you've seen, obviously, from the video, and I will go through more detail, this was a successful test that was very uneventful from the turbopump. So I'll pass it over now to and my colleague Andre to cover some of the details.
Thank you, Max. Hello, everyone. I'm Andre Ivankovich, lead engineer at Launcher. And today I'll talk a bit about the analysis and manufacturing of our E2 LOX turbopump. So before we got into manufacturing, we worked with Ansys to simulate the performance of our flow path in our LOX pump. And so we wanted to do this to ensure that the predicted performance was in line with our desired parameters for the entire rocket engine system. So a few examples of the different parameters we analyzed are pump efficiency, pump head, which is the output pressure of the pump. And we also did a cavitation analysis of the pump. So in terms of efficiency, we simulated that we would achieve an efficiency of 65 to 67% in our LOX pump. And a competitive benchmark for pumps of similar size is about 60. So 65 to 67 is very good. So we used Ansys CFX to simulate the entire flow path of the LOX pump and output the pump head changing with each rotation in time. So that's what you see on the plot on the bottom left, and that showed that the predicted output pressure is where we want it. And then on the plot on the bottom right, we performed a cavitation analysis. And so cavitation is basically when the pump pressure to the inlet of the pump drops too low, bubbles can start to form in the flow path. And this can lead to significant problems because either the pump doesn't perform like it should, so the output pressure will drop, or it can lead to failure actually if the pump no longer pumps anything with cavitation stall, and then you'll actually overspin the pump. So with the cavitation analysis with Ansys CFX, we simulated how lowering the pressure to the pump input affects the output pressure. So that's what you see on the plot on the bottom right. And what we simulated is that the cavitation performance will be in line with what we desire. And so the reason this is important is you want to see how your pump will operate at low pressures. Basically, if your pump can't operate at low pressures, you'll have to add weight to your rocket, either through a booster pump to the LOX pump, or you would need thicker walls on your rocket to contain the higher pressures needed to feed your pump. So we can go next.
Yeah, no, two quick points. So we, with the Ansys CFX, we did full rotation analysis, and obviously we have great visual that we can't show due to ITAR concerns. So these are some of the elements we can show. So today we can't show you the actual inside of the impeller inducer. The original pump had a booster pump, the heritage pump, and so we successfully reduced the inlet pressure from about 10 bar, and we've proven it and tested it at 3 bar during the test campaign. And that's due to obviously both an innovative inducer design with variable pitch, more modern than the original one, but also the analysis to validate it with Ansys CFX, and then obviously test it after manufacturing successfully. And it's a significant, the booster pump is not only development time, expense, and mass on the vehicle and the engine, but it also an efficiency drop because it used about 10 to 20% of the high pressure liquid oxygen to actuate that booster pump. And so it contributes to the high efficiency that we were able to prove.
All right, so once we verified that our simulations are in line with what we desire for performance, we moved to manufacturing and worked with VELO3D on using their Sapphire 3D printer to produce some of the components of our LOX pump. So here we have the pump outlet housing, which was printed on the Sapphire printer in Inconel 718. And so one of the reasons the Velo Sapphire printer is so ideal for producing a part like this is because the pump outlet actually takes the high pressure fluid from the impeller and directs it to an outlet pipe through a volute, which is kind of the same shape as a snail shell. And so this outlet pipe on a typical powder bed fusion machine, you would need to design some sort of 45-degree angle teardrop shape because of the low overhang angles in the final part, and then you would need to machine that volute. But with the Velo Sapphire printer, we were actually able to print this part with minimal support structures, just some stick supports, which were easily removable. And we were able to print those low overhang angles in the volute, which was ideal. And so there on the right is the pump outlet housing fitted up with the inlet housing on the bottom.
And the volute is behind this wall, obviously, all around. Were there any support in the volute at all?
There were some stick supports. Yeah.
Removed by hand?
Hand tools.
Hand tools. Great.
And so this is the E2 LOX pump inlet housing, which was also printed on the Velo Sapphire printer in aluminum alloy F357. And so this was a part with very complex internal geometry because it serves the job of bringing in the flow laterally and turning it 90 degrees to direct it into the pump inducer, but it has to enter that inducer nice and uniformly. So the internal geometry of that part is quite complex and has all sorts of low overhang angles and difficult geometries, which are difficult to print with traditional powder bed fusion machines. But with the Velo system, we were able to 3D print this part. And so this part hasn't been tested yet, but will be in the near future. So on the next part, due to ITAR restrictions, we can't show the actual 3D printed inducer impeller. But what this is on the image on the right is a general shape of an inducer impeller from a publicly available research article. And so our inducer impeller was also printed on the Sapphire printer. And so it was printed flat, which I'll get into in a bit here. But basically, just to talk about the purpose of this part, it's rotating in our system at 30,000 RPM. The spiraling blades on the left are the inducer portion, which steps up the pressure leading into the impeller downstream. And the impeller pumps the fluid up to the final pressure, which enters the volute and exits the pump. And so I mentioned that the inducer impeller for launcher was printed flat. And so this was really a unique thing we could do working with Velo 3D because first of all, typically shrouded impellers are difficult to 3D print because that top shroud has a very low overhang angle. And so it's difficult to access any sort of support structure for that top shroud. So what happens a lot is the impeller will need to be angled on the build plate as it's printed. But this isn't desirable because then you can have a non-uniform mass distribution away from your rotational axis. So by printing the part flat, we got a nice symmetric mass distribution of the part relative to that central rotational axis. And so this is ideal for balancing after you print. And so balancing is needed basically because if a rotational component in turbo machinery is not balanced, then on every rotation, there'll be a large vibration that's impulsed into your system and into your bearings. And so an unbalanced part can lead to large vibrations in the bearings. It can lead to bearing failure or limited lifetime due to bearing wear. So what we found by printing the impeller flat is that the initial unbalance was low enough to allow it to be balanced with the design material removal area. And so this was really good news and not always the case with the 3D printed impeller, which can lead to the part having to be scrapped, basically. So on the first try of our produced impeller, we were able to balance it successfully.
And balancing is obviously a required process, and we confirmed also the quality of the balancing in the high-speed accelerometer on the testing. So it was not only successfully balanced, but also confirmed as a very, very stable and high-quality balance at 30,000 RPM.
Definitely. All right, so once we had the parts produced for our LOX pump, we built the actual test article, and that's what you see in the image here. So in the center is that pump outlet housing I was discussing earlier. The left is the inlet housing, and the right is the turbine housing. And so we integrated our E2 LOX turbo pump at NASA Stennis Space Center in cell 2 of the E complex. And so here you have the test article actually on the stand. So the arrow in the center pointing down is actually gaseous nitrogen that enters the turbine housing and drives the radial turbine thereby powering the entire single shaft turbopump. And so the turbine gas is discharged there on the 90-degree turn to the right into the atmosphere. Then on the left side of the article, you have the actual LOX pump, which is being fed from the pump inlet in the flex hose on the left, feeding in liquid oxygen. And the liquid oxygen makes its way through the pump into the impeller, which is spinning and pumped out of the discharge towards the bottom of the screen.
And another key part of the design, this is a single shaft turbopump for the E2 engine. So right here is where the fuel pump will attach on the same shaft in assembly. It's already ready for it. It's currently in design and it will be printed and with all the same method on the VELO3D Sapphire. Given that it's not cryogenic, it's more of a trivial design. It's also less mass flow given the mixture ratio. Liquid oxygen is the biggest challenge. And then, as we mentioned, this housing will also be 3D printed on Velo in Inconel as it gets integrated into the engine eventually. So this is another test of the article, and it's significant because it's a 120-second test. So with this test, we prove obviously the function of the pump and the reliability. You know, we discussed the liquid oxygen challenge and how dramatic a rubbing event can be at this pressure and this rotation speed. And so doing a 2-minute test is critical at nominal RPM and nominal pressure to prove that the article could be integrated with the engine for flight. A typical stage 1 flight, which will be powered by a single one of these turbopump on our E2 engine, the typical flight is less than 2 minutes before engine shutdown and separation. So this is an early version of a qualification test for function and performance of the pump. Any other comment, Andre, on the pump?
Yeah, we were really pleased with the performance, low vibrations, and functioning nominally in a cryogenic environment at nominal RPMs.
And some of the other, and we'll get to 120 seconds. Some of the other significant is that this is our first test article, this is our first test campaign, and while this pump design has been manufactured previously using traditional casting and forging and machining, we obviously manufactured it in the United States using VELO3D for the first time using additive manufacturing, and out of all the first test parts basically, or first prototypes, we're not testing it successfully. So the workflow and the cost of leveraging 3D printing without tooling and the full success of the test campaign, also the efficiency that we've gained, including an improved inducer and no need for booster pump, or significant breakthrough for our roadmap, but also it shows what can be done with this Ansys VELO3D workflow. So that's it. A quick note, on some of the test results from Andre.
Yeah, so some of the key tests we performed successfully with our first LOX turbo pump is a 2-minute duration test, which you just saw at nominal RPMs. And so we actually also did a cavitation performance test that was 30-second duration, basically lowering the pump input pressure over time and seeing how that affects the output pressure. And we saw that the cavitation performance was as we expected. We could run the pump at low pressures, input pressures without issue. We also did a LOX test for a minute duration, and the second half of that minute was ramping down the turbine inlet to assess the performance of the turbine. And so we also did a 33,000 RPM test for 30 seconds with liquid oxygen as well.
And all the long duration tests are done with the low input pressure of 4 bar, right? Mm-hmm. So we did the first test was at 10 bar input, then we did the cavitation test, and then as we confirmed the performance of the inducer, all subsequent tests were performed at the flight-like condition and low input pressure. Thank you again for listening. And this is the end of the launcher portion of the presentation. And I'll pass it over to the Velo3D team.
All right, thanks, Max and Andre. I'm Sunil Patil, and I'm from Ansys. Max and Andre talked a little bit about the simulations of the rocket turbopumps and how the simulations can be used to predict the performance. I will go a little bit more in detail about the design and analysis process for the rocket turbopumps. So here I have highlighted the overall design analysis workflow for the turbopumps. And also on the right-hand side, the typical project schematic you can see within the Ansys Workbench platform. The overall design typically starts with a concept design or the preliminary design, where you provide the duty parameters or the design requirements, things like RPM, which is critical, flow rate, pressure gain, as well as some of the constraints like geometry constraints. And then the preliminary design tool can provide the initial flow path, and that in combination of the blading tools can provide you the flow path with the bladed components like vanes and inducer and so on. And this is what I'm showing here on the left-hand side. Now what you can do, this is just the initial starting point. You can define various design parameters. Anything you can think will optimize the performance of the turbopump. Things like the impeller radius, or things like the angle, the blade angle, and the blade thickness distribution, axial length, and so on. You can define all these parameters. And once you have this geometry ready in a parametric way, you can go on performing the analysis. The intermediate step involved is the mesh generation, and the tools like Ansys TurboGrid can be used to create an automated mesh in the flow path, and that can be used for the CFD analysis. So after the mesh generation, the CFD and structural analysis can be done. CFD analysis provides the overall performance, while the structural analysis, mechanical, can be done to test the structural integrity of your design. And apart from the pump performance, you can also get a lot of colorful plots, which are fun, but also provides a lot of insights, engineering insights into your design. And the same workflow can be created, as I mentioned, in the Ansys Workbench platform by connecting these different tools which can do these different steps within the design. So for example, this ADT Turbo Design tool was used for preliminary design, which is then connected to TurboGrid for meshing. Then it was connected to CFX for CFD analysis. And it's flexible in the sense you can add and remove components. You can add, for example, mechanical for testing the structural integrity and so on. So the rocket science, sometimes can be daunting, but simulation helps to at least make the design process of the critical components of the rocket engine relatively simple. Now I'll talk a little bit about the pump performance, which Andre talked. So how we can predict the pump performance. You don't necessarily always have to start with the preliminary design. Let's say you have some kind of a drawing, or you have a CAD data. You can collect all that input data in terms of the geometry and the operating conditions. And then you can still use the same set of tools I mentioned in the previous slide to generate the meshes and build the CFD setup. And here I've shown a typical CFD setup in Ansys CFX, where you have to ensure some of the key ingredients like the real fluid modeling, a proper turbulence model, a cavitation model, and high performance computing to get results really fast. And then in Ansys CFX, you can actually get the operating condition in simple CSV file or Excel file. And this setup basically can be run for all of the operating conditions to give the performance curve for a given machine. So this is the performance curve for the turbo pump. And plus, you can also get any additional post-processing details. So that's the overall process, generic process going from the input data, input CAD or geometry to getting the performance for the turbo pump. Now we'll talk about cavitation, and Andre mentioned the importance of cavitation. If you have cavitation, the pump will not perform properly and in fact can cause failure, a substantial failure. And hence it's important to predict the performance from the cavitation perspective. You want to make sure during the design stage that the cavitation will not happen or will happen in a very less form in the critical operating range. So here I'm showing a NASA rocket pump inducer where they observed the cavitation at certain operating conditions. And so we took that case from NASA and simulated that in Ansys CFX with the Rayleigh-Plesset cavitation model. And you can see here, we were able to predict the cavitation quite accurately. You can see visually the cavitation. So not only just the overall qualitative performance, but you can see here that this pump performance from NASA, which is in green, their test performance, and the other two lines are from the CFD analysis with CFX, where you can see this drop in head is predicted very accurately using the cavitation model within Ansys CFX. And as I said, this is very critical, especially in the design phase itself. You want to make sure the cavitation does not happen, especially at the critical operating range or critical operating points. And finally, I'll talk about the design optimization. For any machine, you want to optimize the performance, and especially if you have a choice for additive manufacturing, which gives a lot of flexibility in terms of how you can design it. Provides a lot of flexibility in the design space. So you can use the same kind of workflow I mentioned in the first slide, where you can use parametric geometry. And here I'm showing some of the design parameters like the blade angle distribution, blade thickness distribution. And once you have that parametric geometry, you can connect an optimization tool like OptiSlang to this workflow, which this tool first can perform a sensitivity study, which can tell how these input parameters can affect the objective. That objective might be efficiency or head or anything like that. And also, more importantly, it can tell, you might have dozens of input parameters. Out of those, how many are the most important ones? So for example, out of many input parameters here, you can see in this particular case, the impeller radius and one of the blade angles was the most important parameter and had the most impact on the efficiency. And then that creates a meta model, and one can perform a quick meta model based optimization, as shown over here, to give the final optimized design. So this was the optimized inducer impeller of represented a rocket pump, which was obtained after about 200 design point study, which were run concurrently for about a 3 hour of total wall clock time to get the optimized design. So in a quite reasonable time, you can start with the initial design and optimize your turbopump design fairly quickly. I just wanted to briefly mention about the Ansys startup programs. We realized the startup companies, which Launcher was in the previous few years, have big ideas, really great ideas, but sometimes limited budget. So we provide startups our software, like the CFD and mechanical software I talked in this talk, but also some of the other software related to electromagnetics and embedded software and so on at a highly discounted price. So that really helps to accelerate the design cycle and reduce the physical testing efforts. So if you think you're eligible, please reach out to us. Thank you, and I'll pass it to Gene.
Thanks, Anil. So now here we come to the point where we take all the slick stuff that Launcher did, that Ansys did to optimize their design, and we actually have to make the part. And the worst thing, the last thing we want to do is go back and say, nope, we can't build this, redo something. And in this case, we didn't have to do that at all. We took the geometry as optimized, as designed, and printed without compromise. So on a real high level, what is laser powder bed fusion? It is the iteration of laying down a layer of powder and selectively melting layer by layer the material that you want to become your final part. This is done through a cylinder and piston design where the piston steps down an iteration each layer. We then recoat a thin layer of powder on top of the substrate and then selectively melt the material that we want to become the final part. And this is done over and over again until the final part is built. So typical in metal AM, we need to add supports to specific structures. In this case, we're kind of highlighting long overhangs. And you want to print this long overhanging arch, but without having some constraint or support material. The tendency is for these internal stresses to compound upon themselves, warp upward, and actually make recoating impossible, and thus terminating the build. So the typical solution in the world of metal AM is to add support material, and that's what we're showing here by the red pins on the right-hand side. This will keep that structure constrained and well supported and avoid the tendency of the material to succumb to internal stresses, warp upward, and essentially terminate the printing process. This is something that Velo3D has a really unique capability to avoid this support material. And again, we can't show the exact shrouded impeller inducer that we printed for Launcher in this case, but this is representative of that part. On the left-hand side, we're showing a cross-section of that shrouded impeller, and the red that you see there is all the support material that a conventional metal AM system would have to add in order to print that top shroud successfully. Or you work around it and tilt the impeller, and as Andre mentioned earlier, that's undesirable because you run into problems with balancing. And really, ideally, you want to print this thing flat. You want to print it with no support on the inside, so you don't have to post-process or remove a bunch of messy material on the interior of the part. So what Velo is capable of doing is printing this impeller flat on the build plate. You're going to get good circularity. You're going to get no added support material that has to be post-processed or machined away or removed after the fact. We only put a constraining wall around the OD of the impeller and then turn that off in a single lathing operation, and you're left with your final part. This is all enabled by our full stack solution. A lot of other platforms out there just will support the printer and not necessarily much else. We take the process from the beginning of the print preparation software in Flow, where the user will import a CAD model, will orient the part in 3D space, will add support material where necessary, and then actually prepare a print file, which is then loaded into the Sapphire. And that is our family of 3D printers that can read any type of file. And we don't have calibrations for machine specifics. It's one print file and it will work on any 3D printer anywhere in the world. And you'll get the same result. So that print is then, like I was mentioning before, undergoes layer by layer melting of metal. And throughout the build, the machine is monitoring the entire process through around 800 different sensors. And that is all compiled and read in our Assure quality validation software. So all of that is put together. It can be monitored in real time and also put together in a comprehensive build report to really assure the end user of the quality of the part that they're receiving. It's also really great for troubleshooting any anomalies that occur in the build. We have a really unique opportunity to pinpoint those and see what if something did go wrong. So getting back to Flow, our preprint software, what does it take to really do this on a preprint software level? The Flow software is intuitive enough to recognize geometry and apply laser parameters accordingly. In this case, we had some vertical walls. We had primarily low angles on the top shroud. And then we had some bulk film that we wanted a high throughput so that the print could be happen as quickly as possible. So the Flow software will recognize these low angles and apply the low angle process to the top shroud. It recognizes these big bulky sections and puts a high throughput core parameter on those areas. As well as vertical walls for surface finish, you automatically recognize them and put a fine surface finish on the vertical walls. And all of this happens automatically. This isn't something that the user has to pay attention to. This is all done behind the scenes by Flow and is all generalized in our software. So really, what does it look like? I've seen a lot of other folks out there printing low angles, claiming they can print low angles, but I never see a picture of what that surface looks like. And this is a really challenging, not the actual geometry that we printed for Launcher, but this is a very low angle, near 0 degree angle of overhang on a top shroud. And we print this down to about 15 micron SA on that downskin surface. This is something that I haven't seen anyone else really advertise or quantify that surface finish of that downskin process. So how do we really enable this in the print side? In the machine, in the software, we do all these cool tricks, and then we take it to the printer, and this is where our non-contact recoder takes over and really enables the full potential of these laser processes. Velo does things a little bit uniquely different. We do not smear powder across the powder bed. We don't contact the part with the recoder every layer. We will gently snow down a thick layer of powder. This is about 1.5 to 2 millimeters thick. And then a normalizing blade, a secondary step, will flatten out that surface. And then it is addressed by our proprietary powder removal tool, which removes all but 50 microns of powder from the substrate. So then at that point, the substrate is ready to receive laser commands and melt selectively the material that you want to fuse into the part. This is all quantified and checked, every single layer, by a structured light scanner. Again, that's all available in the Assure build report so that every layer can be inspected and quantified after the build. So here we're showing a generic shrouded impeller and how it prints. The part starts as a solid base where that bulk fill material is applied to the thicker sections. And then you see that vertical constraining wall grow around the outer diameter. And now we're just beginning the outer edges of that top shroud, and everything's growing inward on itself. And the internal stresses really play in our favor here because we can print extremely low overhangs without the need for support material. And this shroud, as you can see, there's no added support material in there. This is going to print free of support and finish out without any support material that needs to be removed after the part is printed. So I'll give it back over to Max to talk about the summary of what we talked about here today.
Great. Well, thank you. And thanks again for the 105 people there. By the way, we are growing very rapidly. So if anyone is interested, we have a careers page on launcherspace.com. But yeah, wrapping it up, ourselves have been, the biggest challenge when we received the heritage design we licensed was first, manufacturing. How are we going to make it? And obviously 3D printing was our goal, and we knew about the Velo3D supportless technology, but that's just marketing and theory at that point. And it's been incredible that we were able to successfully do it on the first prototype, and basically receive parts that were at the correct dimensions and material properties were even better than expected after heat treatment. Now that's still, theory, right? We have the parts, they look right, some testing and some dimension inspection, but to then take that for the first time, a 3D printed version of this part, and put it on a test stand and get a full test campaign of many minutes beyond what would be needed in real time, perform successfully with liquid oxygen. And this is again a staged combustion pump with 4,000 psi discharge, and reaching our efficiency goal, has been to say the least better than expected, right? That doesn't happen like this often, or at least maybe ever. And that was made really possible by the combination of obviously using Ansys CFX to predict and confirm a lot of the design. While the pump is heritage design, the flow path is customized, and we also talked about the input pressure and the inducer optimization. So the power of simulation with Ansys, and then the power of manufacturing without support with Velo3D had made this this test campaign, this program, this project as part of our E2 development possible. The key is also that we didn't have tooling expense. We didn't have a very complicated supply chain for traditional, casting and forging. We had great material properties, and great balancing. But we also have a workflow that it's easy to iterate. The design that we took is, for example, designed for traditional manufacturing. We have a bearing cooling passage inside the inlet that are designed for traditional machining, and have kind of ports you plug in. There are opportunities to turn these into a better geometry for 3D printing, since we can print them. And so we're in a spot where we've proven the traditional design. We did not have to modify it. But every print we make, there's no retooling. We can make slight modification and improve anything we think we should test or improve. All of this made possible by the partnership. Obviously, we also have a great partner with the sponsorship from the Space Force and with NASA for testing. And then I've been with Andre answering the Q&A as best as we can, and I'll resume doing that. I don't know if Michael, you want to verbally cover them while we do that. So.
Yeah, we're getting real close to the hour. I did see a number of questions around service finish and post-processing. So I think we could maybe go into those a little bit and answer them verbally. So if you could comment a little on if you compared it to casting, I think that was one of the questions, and with regard to the service finishes.
Yeah, there was no measurement made, but based on our chief designer experience with the traditional heritage design, he deemed it as Igor Nikishenko. He deemed it as equivalent, or maybe even a little better than what he has seen on the traditionally produced version. And what's important is our first test campaign. We used non-honed, so as printed volute surfaces and shrouded impeller surfaces. We did produce a second impeller with Velo, and we did add the cost and time in the workflow to get it honed for I guess a better surface finish. And we do plan to test that and see if we even have better efficiency and decide if long term we will do that. But obviously we are at the nexus of high performance and low cost. So anything we can remove from the process that doesn't impact performance materially, we usually are takers.
Yeah, I think from the images, it's pretty clear on the volute section. There's some post-processing and machining that was done for mating surfaces, it looked like mainly.
Oh, sorry. No, a lot of machining for, bearing clearance, right? Very critical. Various thread, flanges, anything else, but yeah, not on the wet surfaces. So my comment was about the parts that are inaccessible. Obviously, it's still 3D printing. We have to cut it off, use hand tool to remove support, heat treat and hip and other type of thing, and then before that machining, for key clearances and tolerances for mating surface. The bearing is also key, and obviously we key part of this technology are bearings and integrating them.
Gene, there's kind of one for you, and then we'll get some closing thoughts at the end of this. What methods or techniques were used to print the impeller flat without internal supports?
Well, I can't get into the proprietary laser parameters or what we're doing as far as the laser processes. I can tell you that we are playing some tricks with laser movements and laser powers in order to manipulate melt pool sizes to be more desirable for low angles. And really, that is all done on the Velo side as far as process development and test prints, and that's rolled into the logic that is found in Flow. And that is something that comes with Flow license. You can just use this by clicking prepare, and it does it. So it really takes a lot of the responsibility out of the user's hands. It just makes it easy.
All right. Well, yeah, thank you very much. We are up on time, and so I just wanted to get some last minute thoughts. Max and Andre, maybe you guys can kick it off for us.
No, thank you again. I think we covered how unique this partnership and this technology combination is in the development of liquid rocket engine turbopump, and we're very excited to share it. I'm sure many people, and we know some of you from the Q&A, are in the industry, and it's great to see if we can help contribute to advances in industry through sharing within obviously the confine of ITAR. So thanks again. Thank you.
Sunil, any closing thoughts from you?
Thanks for the opportunity. It was, as Max mentioned, was a great topic of interest to a lot of people in the space industry. So was happy to present this unique combination of design optimization and additive manufacturing for the turbopumps. Thank you.
All right, Gene, I'll let you close it out.
Yeah, I'm really privileged and honored to be a part of this effort. And, it's something new and the ingenuity that Launcher is bringing to the table and really doing something unique here. I'm really proud to be able to enable that and really just kind of stand on the shoulders of giants because, they're the geniuses, they're the smart ones. My name's Gene and I just print stuff. So I'm really, really honored and privileged to be a part of this effort. So thanks, really looking forward to seeing what else you guys have in the future.
All right, thank you everyone for joining us today. Have a great rest of your week and stay tuned for more sessions from VELOVirtual as we dive into further applications. Thank you very much.
Thank you everyone, have a great day.
Thank you.